And so now Daniel has muted everybody. So during the talk, you can ask questions. So if you want to ask question, you could either unmute yourself and ask, or you can ask question in this chat. Then I'm gonna read your question. And also this session is now being recorded. So be careful. If you say something stupid, it will be recorded. It will be on YouTube. But you know, after
me?
you are on YouTube always. Anyway, so and after this, we will have official discussion session, which will be also recorded. But after that, Daniel will stop recording. Then you can say anything stupid. So if you want to say something stupid, wait for that. Okay, so it is our great pleasure to have Hugo Duminil-Copin today in this seminar series. And I think Hugo doesn't need any introduction. He's one of the world leaders in mathematical physics. And if you are interested in hours and honors, please look up his Wikipedia. You will find a list, a big list. I checked it last night. Okay, and of course, Hugo has done many beautiful things. And today, he's going to tell us about his recent work with Michael Eisenman. By the way, Michael Eisenman is here tonight with us. I'm very happy about that, about 504 triviality. And I think all of you know about this, but this work is a continuation of the very famous work by Michael Eisenman and Jürg Fröhlich back in early 1980s. Was it 1981 or 1982? And at that time, it was the triviality was proved only for dimensions strictly larger than 4, and the marginal case d equals 4 remained open for quite a long time, even though many mathematical physicists, I think, tried to solve this. But anyway, it has been solved. And one wonderful thing about this history of modern mathematical physics is that Hugo was not born when these papers by Michael and Jürg were published, and we were excited about that. That's really wonderful. Okay, so Hugo, please start.
Well, thank you very much for the nice introduction. And yes, indeed, I was, not born at the time, but maybe already excited about it. I don't know. I don't remember so well. I realized by the list of people that maybe I planned a way too general talk. So what I'm going to do is I'm going to do the first part anyway, which is stating the result. And maybe we are going to do a poll after that, meaning do I explain a little bit more the background, which usually it's what I do, but maybe to this audience it would be a waste of time. So then we can maybe go a little bit more into a little bit more details on the proof, but I mean, not much, of course, in 1 hour, but still a little bit more. By the way, for people who are interested in a really more complete description of the proof, even though it will not be the full proof, I'm actually giving a series of lectures this week. I gave a lecture yesterday and have 3 more lectures during the week. And the lecture of yesterday basically covered what I'm going to talk about today. So the next lecture is tomorrow. It's this, this one-word probability conference or summer school, I don't remember. I can give you the link later. And if you are interested in the proof, I encourage you to look at the other lectures because I'm going to really present basically the full proof. So that's the second point. Okay, so Gaussianity of the 4D Ising model. It's a joint work with Michael Eisenman, and here I wrote 4D Ising model, but indeed we also cover the 5-4 lattice model. I will go back to this later. And usually I present this, result by explaining that it is interesting from 2 points of view, and it's interesting in different ways. One point of view is it's interesting as description of a critical phenomenon in statistical mechanics, and that's the one I'm going to present first. And usually I spend time explaining what are the implications from the point of view of Euclidean field theory. But maybe this is the step that I'm going to skip and try to give you a little bit of details on the proof, because I'm now worried that I didn't target the audience properly. So let me anyway start with the first point of view on the results. So the the statistical mechanics perspective. And again, maybe I'm going to go a little bit faster than usual, because many people know all these things better than I do. So you consider the Ising model on ZD, and we are going to restrict ourselves to nearest neighbor ferromagnetic Ising model, even though probably some of the results would extend to longer range, but you would have to modify the results accordingly. And thank you, Daniel, that's very nice. So you take, just to define that we have the right notations in mind, you take a finite subset of ZD, you look at plus minus 1 to the lambda configuration, so the standard spin configuration for Ising. You look at the Hamiltonian, which is minus sum for x neighboring 1 of sigma x, sigma y. So that means that x minus y is equal to 1. The norm is equal to 1. So these are the neighbors on the hypercubic lattice. And you look at x. By the way, I'm working on the hypercubic lattice. With a student, we are also looking at all the lattices. And in particular, I think there are many nice applications, but maybe I will get back to that later, not to confuse, but for instance, on hierarchical lattices. So you take now a finite volume Gibbs measure, which is given by 1 over norm times the sum for sigma in plus minus 1 to the lambda of x of sigma exponential of minus beta h of sigma, where beta is our inverse temperature. And here, x is an observable. So it's just a function from this to c. Okay? So this gives us Ising Gibbs measure. I'm not going to spend any time on that because this is very classical for, I guess, all but a tiny proportion of the audience. And I will also denote by, like that, the infinite volume measure. Okay, so the limit when when lambda tends to infinity, tends to ZD, of the finite volume measure. Okay, so this is our infinite volume measure, and you all know that the Ising model has this very nice property that there exists a critical point above which the spin-spin correlations converge to m of beta squared when x goes to infinity. If you want, they are always larger or equal to m of beta squared, which is strictly positive. And below, sigma 0, sigma x decays exponentially fast. And here, just to, decays exponentially fast. And here you can even define a correlation length, which is the limit when n tends to infinity of minus n over log of sigma 0, sigma n 0, 0, beta. So why do I talk to you about that? So there is this phase transition between a place where you have ordering and you have positive magnetization and a place where you have exponential decay and where the correlation length psi of beta is finite. I talk to you about that because these two quantities are going to be involved in the main statement of the theorem. Okay, by the way, Michael Eisenman should be able also to answer questions on Zoom, on the conversation. So don't hesitate to ask as many questions as you want. We are 2 at least to answer them, so we should be able to keep answering questions. Okay, so what are the questions that people usually study? So what do we want to study? So as a statistical mechanics, statistical physicists, we like to study the behavior of thermodynamical quantities of the system. So the first example of quantity we want to be studying is how, for instance, psi of beta or m of beta behaves when beta tends to beta c. For instance, the magnetization of beta was proved to converge to 0 when beta tends to beta c. It's what we call a continuous phase transition. But how does it behave? Does it behave like beta minus beta c to some power, etc., etc.? This is the most classical maybe questions you can ask on the critical system. What are the critical exponents of the system? A second example, which I want also to mention, especially if I tell you a little bit more about the proof, is we can also look at correlations. So endpoints correlations in the system, in the critical system. Typically, and that's the simplest one, look at sigma 0, sigma x at beta c, and see, for instance, that it behaves like something like that. So that it behaves like an inverse of 1 over the distance to some power, and that the power should be d minus 2 plus an exponent eta. Okay, that's another type of example of what people want to understand. There is a third type of example of properties that we would like to know, is what is the behavior of large scale averages. What do I mean by that? Imagine that I define the following average of the field sigma against a function. I define it as the sum for x in ZD of f of Lx times sigma x, where f is, say, a compactly supported continuous function. Okay, you take your favorite function, compactly supported, continuous, and you just average sigma x against the blow up by L of this function. Okay, so that gives you a random variable. This is a random variable. And you would like to understand the behavior of this random variable. So is it Gaussian? Is it different? What is the tail, etc., etc.? Okay. There was a theorem a long time ago, indeed. I mean, maybe I should not be saying that, but by Eisenman in '82 and by Fröhlich the same year, independently, that proves the following. They said if you fix d larger or equal to 5, then for every function which is compactly supported, if you look at L smaller or equal, if you look, at beta smaller or equal to beta c, that's the first constraint. And if you look at L smaller or equal to psi of beta, that's the second constraint, then you have the following. So the following is going to say it's a probabilistic way to measure how close T of L f of sigma is to a Gaussian random variable. So I'm going to write it like that. E to the z times T f L of sigma when I average, the characteristic function, or the Laplace transform of your function, it's equal to e to the z squared over 2 T f L sigma squared, beta. So this would be, if I would stop here, I would exactly have, if this would be true for every z, then for every z, if I would have this, or let's say even for R, this would exactly mean that TFL of sigma is a Gaussian random variable. It's a Gaussian. It's a Gaussian of variance, well, the variance of my observable. Okay? So here it's not quite true that it's a Gaussian, but it's very close to being a Gaussian in the sense that the error is of the form a constant that depends only on f. F is fixed, right? It doesn't, so a constant that depends only on f. Z to the 4, you can forget about this thing, but the important thing here is that you were getting a L to the D minus 4. So that means that the larger the L, the closer to Gaussian you are, to a Gaussian. Note that you have this small constraint here that you want to be smaller than the correlation length. So if beta is smaller than beta C, strictly, the correlation length is finite. So you cannot take L arbitrarily large. Okay? But for instance, if you fix beta equal beta C, then you can, I mean, the correlation length is infinite. So this second condition here is inoperant. It's a trivial condition. And you can take any L. And in particular, if you want, you can let L tend to infinity, take what we call the scaling limit, and you obtain that the averages in the scaling limit are Gaussian. So in particular, from this, you deduce that if you have a limiting field, it has to be Gaussian at criticality. Okay? Why do why don't I restrict myself to criticality? Because there are many possible limits that you could try to get by taking L and beta, I mean L to infinity and beta to beta C at the same time. And you get interesting possible limits by doing so. So this is the result. So again, maybe the go home message is that TFL of sigma is roughly a Gaussian, and that its variance is, of course, this. By the way, I mean, it's very easy to see that TFL of sigma is centered because I'm looking at the free boundary conditions. Okay, so the second moment is also the variance. Okay, so this is telling me that TFL is roughly a Gaussian when L tends to infinity. I mean, it's closer and closer to a Gaussian when L tends to infinity. Okay. Let me give you some remarks on this result, which is what happened for D equal 2. Well, for D equal 2, one can prove that it's non-Gaussian. Okay, it's non-Gaussian, meaning that it doesn't get closer and closer to Gaussian when L tends to infinity. And I recommend, it's a beauty. I mean, you see, it's typically the type of result, I mean, that you can deduce from, for instance, Honzager solution, or you can deduce from conformal invariance, but you actually have a 3-line proof. I mean, depending on the length of your line, but I mean, roughly 3-line proof by Michael Eisenman in his 82 paper that I really recommend. It's an absolutely beautiful piece. And it basically says that the quartic, the fourth moment is smaller than twice the second moment squared. And it's not close to 3 times the second moment squared of your observable, which would be the case if it was Gaussian. So beautiful argument, I highly recommend. So I will just cite Michael's argument, even though you can find, you can prove non-Gaussianity using older results, but I mean, definitely in a harder way. The conjecture is that for D equals 3, this is wrong. And here there is a nice paper about giving numerics and also connecting all these questions to conformal bootstrap by Slava Ryzhkov and his co-authors. So here I recommend a recent paper by Ryzhkov. I don't remember, maybe 18 or 19, something like that. On, I mean, it's easy to find. You just Google non-Gaussianity of 3D Ising model, something like that. So it's expected to be non-Gaussian, but it's only conjectural. We don't know yet how to prove that it's non-Gaussian. It remains one dimension, dimension 4, And ironically, and that's what I will maybe not be talking about, dimension 4 is the most interesting dimension from the point of view of Euclidean field theory. So I will skip this part because many of you know it. But for people who don't know about it, just think that this was, from the point of view of Euclidean field theory, the most interesting dimension. And that was exactly, I mean, with dimension 3, these were the 2 dimensions that remained open. So there were results dating from 82 that you would get triviality if certain things happen. And that I want to get credit. So Jörg and Michael both mentioned that in dimension 4, you would also get triviality, in particular in a specific case, which is if the spin-spin correlation, sigma 0, sigma x at beta c, was decaying much faster than 1 over x to the d minus 2. So in dimension 4, 1 over x squared. So 1 over x squared is the decay of the green function. And if it decays much faster, and maybe we will even understand a little bit why with the second part of the talk, if it decays much faster, then it's trivial. The problem is that this is a wrong assumption. I mean, the expectation is that actually in 4D, it is of the order of 1 over x to the d minus 2. So I'm perfectly fine with conditional results. They are important. But in this case, even with just a natural assumption, which was that it decays like 1 over x squared, which is the truth, even with this, we didn't really have such a strong, I mean, we had, of course, many indications, but we didn't have a strong argument to prove that you have triviality. Okay. Let me also mention, since I'm not, usually I cite this at the very end of the talk, when you look at the, or maybe, sorry, let me skip that and I will tell you about it in a second, give you a little bit more references. So what is the theorem that I want to be stating, sorry, okay, today, and tell you a little bit more about it in second part, is the following result by Michael and myself from last year, which says the following. It said, if you fix d equal 4, then you also get triviality, and we have this kind of, quantitative bound, which is still looking like, I mean, the statement looks like before, in the sense that I'm also going to look at the Laplace transform. But this time, I'm not going to get something that tends to 0 quite as fast as before. I know I'm just rewriting what I wrote before, but since it's the main result, I think that putting it twice is not such a big deal. So here, the decay is going to be logarithmic with a small power. So there exists a C positive. By the way, we don't control how bad this C is in our paper. It's definitely not the sharp C. It's not the truth. But we get a similar result that we get closer and closer to Gaussian. Okay? So here, this is a result of our paper. And the result actually extends, I mean, the proof in the way it's written extend to the Griffiths-Simon class of Hamiltonian. So this, if you never heard about it, you are not going to understand what this is now. I'm not going to take time to explain it. But the important feature is that you can reach a lot of Hamiltonians and a lot of models from this Griffith-Simon approximation. And in particular, you get the lattice 5-4 models. So what are those? They are just the phi x now, instead of being in plus minus 1, it's in R. And the Hamiltonian is minus sum of phi x minus phi y squared, which looks, I mean, sorry, there is no minus anymore. So this looks like phi x phi y, exactly like before. right? If phi was only taking value in plus minus 1, this up to constant would be the Hamiltonian I defined before. But here you add sum over x of b phi x squared plus lambda phi x to the 4. Okay? And it's a plus. So this interaction here is mimicking a discretization of the phi-4 Euclidean field theory, the phi to the 4 interaction. And the theorem that we have extends there, meaning that you cannot take b lambda and the rescaling of your model. You cannot take a limit in such a way that you end up with something which is non-Gaussian. It's always Gaussian. Okay? I just realized I didn't branch my computer. Give me a second. Like that, you are not going to lose me in the middle of the proof. I will lose you in the middle of the proof, but you won't lose me. That's an important thing. Okay, so you can take limits for the lattice phi-4. It also works. You also have convergence. So I'm going to stick to Ising, but keep on top of your mind the fact that if you are more interested in phi-4, I'm completely agreeing with you, no problem. And there you can extend the results. Why do I want to mention lattice phi-4? Because it's known that when lambda is very small, so when this interaction here is very weak, then you are very close to a Gaussian process, which would be lambda equals 0. And in this case, you have renormalization arguments that were proving triviality, and in fact, even more things. It was proving convergence to really the Gaussian free field, or the massive Gaussian free field when you take double limits where L go to the infinity, roughly at the scale of the correlation length. So there are many people there. I mean, Takashi was part of them. Antti was there. I mean, there are many people. I mean, Bridges, Bauer-Schmidt, Slade in recent years. There are like tons of people. I'm going to forget half of them. So there is no way to make people happy in this type of stories. So I'm going to not write anything, especially if you misspell things, it becomes even worse. And then the whole world hates you. So I'm not going to cite everybody, but I want to highlight just one thing is that when you look at the phi-4, the lattice phi-4 models, so when lambda is very small, you are very close to lambda equals 0, which is GFF. And on the other hand, when this thing here is lambda phi x squared minus 1 squared plus constant, right, which you can tune by taking b equal minus 2 lambda, this is kind of putting a potential at plus and minus 1. It's forcing guys to be close to plus and minus 1. And when lambda gets to infinity, you reach the Ising model. So in some sense, the lattice phi-4 models are interpolating between Ising on one hand and GFF on the other hand. And the known results of triviality and convergence to GFF were in this regime, where you are close to a Gaussian free field. It was renormalization arguments. You start close to your fixed point, and you prove that you converge to it. Here, in some sense, the interest of this work is to cover the whole interval, so even places which are very far from the original fixed point. So it's kind of orthogonal almost in terms of scope. We prove less, but we cover its non-perturbative argument in some sense. Okay, so that was a very, very, very brief summary of the second part to try to get the lattice phi-4, and usually I explain how it's related to Euclidean and quantum field theory, but maybe people would be more interested in having a little bit more clue about the proof. And the only downside I see in doing that is that I didn't prepare anything. So it's going to be completely live. I'm sorry about that. if it starts to be less clear, maybe it was not clear already, but I mean, if it gets even worse, it's because I didn't plan to speak about that. So I apologize. So it's even more important that you kind of interrupt me if I start to be completely ununderstandable, okay? Because I will have harder time to. So an idea of the proof. But I mean, again, I'm not claiming I'm going to give you a very good idea, but maybe just, I mean, a glimpse at what is happening. And in order to do that, I'm going to start from a result. I'm going to try to skip all the tools that bring you to this thing and just remind you about one thing, which is that it's known for a long time. You can find this in Newman, and you have also a beautiful argument by Michael, which is a little bit more quantitative. It's known that in order to have Gaussianity, it's sufficient to estimate the 4-point function and prove that it's very close to the sum of the pairings of the pairwise spin-spin correlations. So what do I mean by that? Define U4 beta of x1 up to x4 to be the spin-spin correlation of the 4 points. Let me drop the beta just because it's going to be simpler, minus the sum of the pairings. So you sum over the pairings, and you write sigma x pi 1, sigma x pi 2, sigma x pi 3, sigma x pi 4. So there are there are 3 pairings, and you subtract this product from the 4-point function. So notice, and that's the first observation, and it's an important one, notice that if the sigmas x are a Gaussian process, then U4 is 0, simply. Because in this case, you have the Wick rule, right? So the 4-point function is written as a sum of the pairings. So what Newman and Newman and Eisenman proved is that if you have a good control on how small U4 is, you actually have a good control about how small U2n is, where U2n will be the correlation between 2n guys minus the sum of all the pairings. With these times you have 2n factorial over 2 to the n factorial pairings. Okay, so it tells you that if for the 4-point function you have a good control, then you have it for 2n, and then by resumming, basically, you end up with this type of statement on the characteristic function, on the Laplace transform, sorry. Okay, so I'm going to focus on U4. I'm going to try to give you a glimpse at why U4 is small. And one hypothesis that I'm going to make, simply because that's the truth, that's what we expect to be true, is that I'm going to assume that sigma 0, sigma x at beta c. I'm also going to focus on beta c. Let's focus on beta c. It's sufficiently interesting anyway, and it will give you a good idea of what is happening. So I'm going to assume that sigma 0, sigma x at beta c is of the order of the green function. It's decaying exactly up to constant, like 1 over x to the d minus 2. Okay? Of course, I am for d larger or equal to 4, otherwise this is wrong. But for d larger or equal to 4, that's what is expected. It's expected that the spin-spin correlations decays like that. Okay, so how did Michael and Jörg prove triviality in dimension 5 and more? What they did is that they derived the following 3-diagram bound. So what is this bound? This bound is saying the following. It's saying that U4 of x1, x4 is in fact smaller or equal in absolute value. So U4 is negative. This is Leibovitz inequality. So it's really a lower bound that you want, but in order not to get confused with negative things, I'm going to put absolute value. So the absolute value of U4 is smaller than twice the sum over x, like I sum over the whole lattice, sigma 0, sigma, oh, what did I do? Sigma x1, sigma x4. Okay, so this is called the tree diagram bound because you have 4 points and you are kind of summing correlations to a single point x, which varies over the whole lattice. Okay, imagine for a moment that you prove that. I don't want maybe to be discussing how you prove that for now because I want to be controlling a little bit my time and not run into a lack of time at the end of my talk. So I prefer first to ignore how I got this. But from this, what you can notice is that if you plug, so assume that x1 up to x4 are at mutual distances of order L, like, you know, pick points at distance roughly L of each other, maybe L over 2, maybe 10L, but roughly at distance L. Then the bound that we get here gives us that U4 is smaller or equal than the sum over x of 1 over x minus x1 to the 2, 1 over x, or d minus 2, sorry, 1 over x minus x4 to the d minus 2. And when you sum that and you compare, when you sum that, you end up with something which is big O of L to the minus 4. I'm going to go back to that, to the d minus, sorry. You get big O, so of L to the 2 minus d. And you get an additional L to the 4 minus d. So why is this interesting? Because notice that U4 is this thing. So it's in particular, if I look at this and this, these two guys, this is, if x pi 1 and x pi 2 are roughly at distance L of each other, this is of order 1 over L squared, 1 over L to the d minus 2, sorry. And this guy here is also of order 1 over L to the d minus 2. So this term here is exactly of the order of a product of two spin-spin. But this additional term that I get here, this L to the 4 minus d, tells you that U4, in fact, in dimension 5 and more, is much smaller than the product of two spin-spin. So this allows you to derive triviality in dimension 5 and more. Okay? Okay, but you see, bad luck, when d is equal to 4, the green term is exactly of order 1. It looks like a small thing, but it's of order 1. It's not tending to 0. So how can we improve? By the way, I'm sweeping under the carpet here. I'm really using the hypothesis that I'm of order 1 over x to the d minus 2. So I want to be using this hypothesis because I want you to have a vibe at the dimensional analysis that we are doing. But you don't know that. Even in dimension 5, you don't know it's of order of 1 over x to the d minus 2, at least for the nearest neighbor. So you need to be a little bit more delicate in the way you do. But fortunately, Michael and Jörg were more delicate in the way they did it. And you really get the result without assumption. So I'm not claiming that the assumption is necessary to get the five-dimensional case. So what do we need to do to get dimension 4? Well, before that, maybe let's try, let me state what we need to do and then give you a reading at what I wrote. So what we need to do is to improve this tree diagram bound. So I'm going to state an improved tree diagram bound. Then I will tell you a little bit where this tree diagram bound comes from and where the improved one comes from. But for now, I'm going to just state it. So U4 of X1, X4, I'm going to prove that it's smaller than, let's re-put the same term as before. But here, I'm going to add a bubble diagram type quantity. So what does it mean? Okay, I'm at criticality, so let me drop this. So I'm going to add a certain quantity, which is defined as follows: BL of beta C is equal to the sum over X in lambda L, so in the box of size L, of sigma 0, sigma X squared. Okay? So this is a quantity that is very classical in infinite volume. You take the sum over everybody of sigma 0, sigma X squared. And when this thing is finite, it's the beginning of a beautiful story. In particular, one can use the less expansion and so on to prove many things on the model. I also recommend reading papers by Michael from the 80s, where he derives mean field exponents from the assumption that this bubble diagram is finite. Okay?
So Hugo,
yes?
What is L here?
Sorry, you are absolutely right. So X1, X4 at mutual distances at least L.
Okay. Yeah.
Thank you very much. Sorry about that. You see, I should have prepared. I'm really sorry. Yeah. So L is the minimal distance between the different points. Why is this thing interesting? This thing is particularly interesting because in the case where you have the hypothesis, so when you decay exactly like 1 over X to the D minus 2, BL of beta C is, well, it's order 1 if D is larger than 4 strictly. So you don't gain anything when D is larger than 4. It's not really better than the standard tree diagram bound. But in dimension 4, you really gain a lot because this becomes of order log L. So if it's of order log n, then this term here becomes log n to some power, and that's exactly the log L to some power that you are getting in the approximation of the Laplace transform by the result for a Gaussian random variable. So this is the same log L to a power. Okay. Let me try to tell you a little bit how you get to the tree bound. And I'm going to be doing something like I'm going to have to be, you are going to have to believe me, which maybe is not such a good idea, but everybody is at home, so you are basically safe. And you are going to believe me that U4 of X1, X4 can be expressed as an intersecting probability of what we call random currents, but let me just say as an intersection probability of two sets. So it's smaller than 2 sigma x1, sigma x2, sigma x3, sigma x4, times the probability, and I'm going to tell you a little bit more about this probability measure. You have your 3 points. Okay, I don't know how to count up to 4. And also I just said 3, so I mean, I already gave 2 talks today, so I'm a little bit tired. The intersection probability of 2 random sets. One is a random set which connects x3 to x4, and one is a random set that connects x1 to x2. And here, U4 is related to basically the spin-spin correlation between two sets. I mean, you choose one of the pairings, and then you multiply that by the probability that this random set, these 2 random sets intersect. So what are these random sets for people who want to understand that? So the red and the green, they are what we call the clusters of x1 and x3, x1, x2, sorry, and the other one is x3, x4. So one is, this is for the green guy, and this is for the red guy. It's a cluster of these points in what we call the random current representation. And for people, maybe this is not talking too much to some of you. Maybe some of you know a little bit better the Bridges Fröhlich-Spencer representation of spin systems. And you can think, if you prefer for this talk, it's fine to think of the BFS random walk between x1 and x2, and an independent BFS random walk between x3 and x4. You look at this BFS random walk, and you look what is at the probability that they intersect. Okay? This is a simplification. It's not quite what it is, but let's look at that. Okay? Why is this interesting? Because if you express it like that, what you can look at is one way of just estimating the probability of intersection of these walks or clusters is simply to bound the probabilities that they intersect by the expected number of intersections. So imagine you bound the probability. So let's call this cluster X, and let's call this one X prime. Or maybe let's not use X because I'm already having so S and S prime. Already have X1 to X4. So the probability is that S and S prime intersect, where I can bound this by the expected size of S inter S prime, right? Now imagine, really let's just imagine for a moment that we are handling random walks, that S is a random walk and S prime is a random walk. So S is a random walk from X1 to X2, and S prime is a random walk from X3 to X4. When I look at the expected number of intersections, well, roughly speaking, when I'm going to sum over X, the probability that X belongs to S times the probability that X belongs to S prime, because I told you that they are independent objects. But then this is very easy to estimate. The probability that X belongs to S is roughly 1 over X to the, 1 over X minus X1 to the D minus 2 times 1 over X minus X2 to the D minus 2. And because I rescale, what am I doing? Yeah, I'm not renormalizing properly here. Yeah, okay. I need to renormalize because it's random walks that are conditioned to go from X1 to X2. So I need to renormalize by this quantity. And for the second guy, I can do exactly the same. And I'm going to get a probability that looks like that. So you see, if you were random walks, these two terms here, they would kind of cancel with those terms, and you will get exactly kind of the product of green functions between x1 and x, x2 and x, x3 and x, and x4 and x, which is exactly what you get here. Think of this as some kind of the green function for the BFS random walk. So in dimension 5 and more, basically, the argument was to say that what I just did with simple random walk, this kind of computation works for BFS random walk. And things really go very smoothly. I must say it's a beautiful piece of mathematics. Okay, now imagine that I'm in dimension 4. I mean, imagine I want to get the improved tree diagram bound. If I do these lines, I end up with an unimproved like the standard tree diagram bound. So how do I get to the improved one? I get to the improved one by the following observation. And by the way, maybe by the following observation is that bounding the probability, let's take random walks again, that S and S prime intersect, bounding that by the expectation of S intersected with S prime is a big waste in dimension 4. In dimension 5 and more, it's not a big waste because typically random walks, even if they intersect, will intersect a finite number of times. But in dimension 4, it's not true. In dimension 4, conditioned on intersecting, random walk intersect many times. In fact, the power of log. So in order to bound the probability that you intersect, you don't want to be saying just bound by the expected number, because the expected number of intersection is of order 1, but for a wrong reason. It's of order 1 because with small probability, it's large. So here we are going to improve this by saying, okay, maybe it's non-zero, but it's small. Or maybe it's large. If it's large, I took log L to the C simply because that's what we want, but you could imagine taking another threshold. It's just that this one is the right one. If you look at this quantity, you can use Markov inequality and bound this by this quantity. And remember, I kind of told you that this quantity was exactly corresponding to this. So if you get the log L to the C, you do improve on the infrared, on the tree diagram bound. Remains to focus on this term here. Maybe, you know, I mean, it happens that this term is the dominant one. But an interesting thing to see is that when you have a set of points, let's say this is S intersected with S prime. For S intersected to S prime to be smaller than 2 to the k, it must be that there exists a point somewhere where there are few annuli around it that intersect the set. There must be a point which is isolated, if you want. There are not so many points around it which are intersecting the set. I mean, many annuli around it that are intersecting the set. So let me be more formal. Imagine that you define ni plus 1 to be ni squared. You are going to see why I want to do that. And I define the annuli between ni and ni plus 1 and centered at x. I will say that x is k isolated if the number of I such that the annuli, let's call it AIX. AIX intersect a set S in S. So if this set is smaller than K, okay? So you say that you are K isolated in a set S if you have few annuli that intersect the set S, okay? Maybe let's not use S but T, just that there is no confusion with what is below. So I claim it's just a very simple and elegant lemma. I claim that if a set has cardinality less than 2 to the k, so if S has cardinality less than 2 to the k, then there are k isolated vertices. Why do I want to be doing that? Because here you see this bound. I don't want to be saying, well, I'm going to bound the probability that the cardinality of S intersected with S prime is between 0 and log L to the C. I'm not going to bound it by the expected size of the intersection. No, I'm going to say there must be a log L isolated vertex. for this to occur. And I'm going to bound by the expected number of such log L isolated vertices. And why is this good? Because if you take a random walk, if you take, two random walks and you make them start at the same vertex in dimension 4, then I claim that in any of these annuli, so let's say X is the origin, in any annulus between scale n and n squared, these two random walks, they intersect with positive probability. So for two random walks to not to intersect in at least log n annuli before reaching distance n, this is very, very, very unlikely. So the probability of being log L isolated is going to be much, much smaller than the probability of simply belonging to my set. So here, if I erase this and I just conclude because I realize that I'm going over time, this, if I bound it by the sum over x of the probability that x is log L, maybe with a small epsilon, isolated in S intersected with S prime. If I bound it by that, I claim that this is much smaller than 1 over log L to some small power. And again, since I'm summing over x, I recover here expectation of S intersected with S prime, which is my green quantity. So you see, in order to bound the probabilities that S and S prime do intersect, I'm kind of splitting in two. I'm saying either there are many intersections and I use Markov inequality, or there are few intersections. But in this case, I need to have isolated intersections, and this should have a small probability to occur. Now, in conclusion, in the last 2 minutes, you can try as an exercise to use this strategy to prove that two random walks going between points at distance L of each other intersect with a probability at most 1 over log L to some power in dimension 4. You can really run this kind of glimpse of a proof that I just gave you. You can really run it into a full proof. It's an exercise to run it for random walk. So it's not really the core of the difficult part of the proof. The difficult part of the proof is that we are not looking at random walks, at simple random walks. We are looking at either Bridges-Fröhlich-Spencer random walks or random currents. It's kind of the same thing in the case of these models. So these random walk or clusters, they are highly non-Markovian. And you should think of it as we are trying to prove this property of random walk for self-forwarding walks, or something that looks much more like self-forwarding walks. So the dependencies are atrocious, they are horrible. And we had to prove two things. We had to prove that indeed in this annuli between Ni and Ni plus 1, two random currents intersect with positive probability, and we did that by a second moment method. And we need to prove some kind of mixing of these random currents to be able to prove that being isolated means that in many annuli you don't intersect and that this has small probability. So it's a way too fast thing, but maybe I hope I gave you a small idea of the strategy of the proof. And I encourage you to look at the paper and to shoot at us with comments or if you have ideas how to simplify the proof. I'm a very big fan of simplifying proofs. So anybody who comes with simplification, it will be absolutely fantastic. So thank you very much for your attention, and sorry for going a little bit over time.
Thank you. Thank you. It was beautiful. And I also like these artistic slides very much.
Thank you very much.
Beautiful. Thank you very much. So let's thank Hugo. And it's a question time. And Daniel has a question on, does the proof also applies to two-component spin models?
Yes, exactly. So that's a very good and very, very natural question. So the dimension 5 and more argument does apply. But the dimension 5 and more argument doesn't use a key property of the Ising model, which is the switching lemma.
So the switching lemma is used in the paper of Michael because the derivation is nicer with it. But you can derive the tree diagram bound without the switching lemma. So as long as you are good with the tree diagram bound, you can apply it to the two-component spin model using the BFS representation. The problem is that here in dimension 4, we are going to use the switching lemma in a very, very delicate fashion in many places, in particular to prove this mixing property. Imagine trying to prove mixing for safe-forwarding walk in dimension 4, like true safe-forwarding walk. This, I think, as for today, there is no chance to be able to prove mixing. For weakly safe-forwarding walk, you have arguments using renormalization, but for the standard one, it seems completely science fiction to me, at least. Maybe somebody smarter can do it, but I definitely cannot. So the switching lemma for the Ising model and for this random currents or this BFS random walk for the Ising model, it really saves the day. Because it, in particular, it allows to prove this mixing property in a very delicate fashion. And I think this is the core of the argument. I don't know how to do it without, but maybe going through simplifications of proof and things like that, maybe one can find a way not to go through that. It's not impossible. But as for today, I don't know. It's a natural thing to try, and I don't know.
Any other questions? So I guess somebody has unmuted.
I think everybody is unmuted, right?
Not everybody, but.
I mean, people thought about remuting themselves.
So Hugo,